Okay. So, we have been looking at Paisali flow. Okay. So, let us move on and start the next topic, which is on capillary flow. Okay. So, as I was telling you at micro scale, because of the large surface to surface area to volume ratio, so surface forces become very important. Okay. And one such important surface force is capillary force. Okay. Capillary, the word comes from the Latin word capillus, which means hair. Okay. So, when you are talking about flow in a capillary, we are talking about flow in a channel that has size of the order of 50 to 100 micron, okay, typical size of human hair. Okay. So, so capillary flow is driven by basically because of the pressure difference around the interface between two different fluids. Okay. And these capillary flows can be better understood with the help of the Gibbs free energy. Here we have a system that has got two different subsystems. We have subsystem 1 and subsystem 2, okay, and they are separated by an interface here. Okay. So, this is the interface. Now, the total Gibbs free energy, would be the Gibbs free energy of two subsystems plus the Gibbs free energy of the interface. Okay. So, before we talk about that, let us discuss what we mean by Gibbs free energy. Gibbs free energy is the energy of a system where the controlling parameters are the thermodynamic parameters, meaning the temperature, pressure and the number density. Okay. So, these are three parameters. If we have a system and it is specified by these three parameters, then the energy of the system can be defined in terms of Gibbs free energy. Okay. So, Gibbs free energy is nothing but energy of a system in which thermodynamic control parameters are pressure, temperature and the number density, okay, N. So, in that case we can call the system energy, we can specify in terms of the Gibbs free energy. So, in this particular system the total Gibbs free energy is summation of the Gibbs free energy for the two subsystems 1 and 2 and that of the interface. If we assume that this system here is in equilibrium, okay. So, if a system is in equilibrium, the Gibbs free energy is minimum for that system. Okay. So, for systems in equilibrium, Gibbs free energy is minimum. Okay. So, now let us say this interface here, okay, this interface, if we specify that the size, shape and the volume of the interface can be represented by a parameter xi, then since we say that this system is already in equilibrium, let us say the system is undergoing a perturbation, let us say xi moves from xi plus del xi, then for that del xi perturbation of the system the Gibbs free energy change should vanish. Okay. Then only we can say that the Gibbs free energy for xi, or let us call it xi 0 as the equilibrium position, is minimum. Okay. So, we say that the free surface defined by xi in terms of position, volume and shape. Okay. So, xi is the quantity, the parameter that is defining the location or the position, the volume and the shape of the interface. Okay. Now, if so, that let us call it at equilibrium, let us call this value at xi 0. Okay. Now, if we have a perturbation, let us say we subject the interface to some kind of perturbation d xi. So, the free surface quantity would become xi 0 plus d xi. Okay. Now, this perturbation d xi should result in vanishing free energy. So, the resulting delta z should be 0. This is because if you let us assume that this is the variation of, let us say this is, we are talking about in this axis g, and here we are talking about some zeta, and this is the minimum, this is the value of zeta 0 at which system is at equilibrium, and there the zeta is zeta 0, right, and g is minimum. Now, if you perturb the system by a small amount delta xi, okay, let us call this as delta xi, since this is the minimum, the change in the free energy here should vanish. Okay. So, dz should be equal to 0, and if dz is not 0, then what it means is that the system attains a new equilibrium position. Okay. So, our original assumption that zeta equal to zeta 0 is the equilibrium position is breaking down. Okay. So, if delta z is not equal to 0, then the interface attains new equilibrium position. At which the g is minimum. Okay. So, this basically breaks down our original assumption. That xi 0 is the equilibrium condition, right. So, in that case we can write delta z, the change in the free energy, as del g over del xi into delta xi, okay, which would be equal to, we have a system of different subsystems. So, we can say I into delta zi over delta xi into delta xi, okay, and this change in the Gibbs free energy is going to be 0, right. So, this is the condition that should be valid at equilibrium. Okay. So, what we learn from here is that if you have a system having different subsystems and an interface, the sum of the Gibbs free energy is to be 0 for that system to be in equilibrium. Okay. So, having said that, next to move on and talk about surface tension. Surface tension is an important parameter when you talk about surface forces, okay, or the physics of surfaces. The surface tension basically arises because of unbalanced forces at the interface between two different fluids. Okay. So, if you look at this surface here, this is a surface between a liquid and a gas, and if you take a molecule somewhere at the bulk of the liquid, okay, this molecule here, it has interaction with the surrounding molecules equally. Okay. So, the free energy of this molecule is minimum. Okay. So, then if you will consider a molecule at the interface between a liquid and a gas, you can see that it interacts with all the molecules, liquid molecules, okay, at the bottom sides, but on the top it does not have the liquid molecules to interact with. Okay. So, there is the molecule here is missing all those molecules at the top, and what that provides is increased free energy of the system of molecules around the interface. So, that gives a tension force at the interface, which is known as, which is basically the source behind surface tension. And what surface tension tries to do is tries to minimize the interfacial area. Okay. So, if you put a drop of liquid at a corner, you can observe that the interface is going to be in a part of a sphere, okay, because it tries to minimize the surface area. So, we can define surface tension, we can define surface tension So, surface tension can be defined as Gibbs free energy per unit area, and that is at fixed temperature and pressure. Okay. So, mathematically we can write surface tension is defined, is expressed as gamma is equal to del Z Gibbs free energy divided by del A at constant pressure and temperature. Okay. So, the unit of surface tension, energy will be Newton into meter, so divided by meter square. So, the unit is going to be Newton meter. Okay. So, that is going to be the unit of the surface tension. Now, if you do an order of magnitude, okay, sorry, this is Newton per meter, not Newton meter, this is Newton per meter. So, gamma is the energy is Newton into meter, area is meter square. So, you get Newton per meter as the unit of surface tension. Now, let us look at the order of magnitude of surface tension. Okay. So, typically the gas molecules have size of liquid molecules or gas molecules, they have size of the order of 0.3 nanometer, that is what we have studied. So, the area will be of the order of 0.3 nanometer square, and the interaction energy between the molecules is of the order of couple of thermal energies. Thermal energy will scale as the Boltzmann constant into temperature. Okay. So, considering that, we have gamma will be equal to 2 K B into T over area. Okay. So, this should scale as, okay, we are not determining the exact value. So, this term here is the Gibbs free energy, which is couple of thermal energies. This is the area of molecules. Okay. So, we can find gamma of the order 2 into Kb will be 1.38 into 10 to the power minus 3 into, let us consider temperature as 300 degree Kelvin, right, minus 23 divided by area is 0.3 nanometer, right, 0.3 into 10 to the power minus 9 square, right. So, if you calculate, you will get this about 90 millijoule per meter square. Okay. And we know that the gamma of water at 20 degree centigrade has been found to be 72.9 millijoule per meter square. So, that gives you a scaling of the value of surface tension for liquid water, and 72.9 millijoule per meter square is what has been calculated. Okay. So, here we look at the surface tension of different liquids. We have water, which is 72.9 millijoule per meter square, then mercury has got very high surface tension, about 486.5, benzene has about 28.9, lower than water, also methanol, okay. And blood has surface tension about that of water, so 60 millijoule per meter square. Now, let us try to express surface tension in terms of how it will scale by considering a fluidic element, okay, of some length and some width. Okay. So, let us consider this is the fluidic element. Okay. Let us consider that we are applying a force here, and because of the force the fluidic element undergoes an extension, right. So, this is F and this is L, let us say this is delta L, and the width is W. Okay. So, the amount of force that we require to apply, that will cause a change in length delta L, will be the amount of energy that would be required to cause that change in length delta Z will be equal to F into delta L. Okay. So, this is the energy required to extend the length of fluid element by delta L. Okay. So, now if you extend the length of a fluidic element, the surface tension is going to increase, right. So, the surface energy is going to increase. So, the surface energy, change in the surface energy delta G will be gamma into the area, right. So, increase in area, which is W into delta L. So, that is going to be the increase in surface energy. Now, if we equate these two, F delta L is going to be gamma into W delta L, then we get that surface tension gamma is going to be F over W. Okay. So, it is the force per unit length that is acting on a fluidic element to extend it by some distance to enhance its surface energy. And as I was telling, the surface tension behave the same way as the tension in a membrane, which tries to always minimize the surface area. Okay. And the cause of capillary rise, as I was discussing in the beginning, is the Young-Laplace pressure drop, okay, which always exists across a curved interface. When the interface is flat, the Young-Laplace pressure drop vanishes. Okay. So, we will try to derive an expression for Young-Laplace pressure drop here. So, let us try to derive an expression for Young-Laplace pressure drop. So, Young-Laplace pressure drop is present across curved interface in thermal equilibrium, and we can derive the delta P surface, the Young-Laplace pressure drop, using a minimum energy condition. Okay. So, let us consider a fluidic element as you see it here. Okay. So, this is the fluidic element. So, initially, so it has dimension in one way delta x, and the other way is delta y. So, this is basically a fluidic element, something like this. Okay. And this dimension is delta x and this is delta y, right, what you see it here, this across this, right. So, this is delta x and this is delta y, right. So, now this fluidic element expands by a length delta z in the direction normal to this surface. Okay. So, it expands by delta z. So, this is the configuration after it expands. Okay. This is the configuration after it expands. Now, if you look at this surface, we have two radius of curvature, one is r1, this is original surface I am talking about, delta x and delta y. So, one radius of curvature is r1 and the other radius of curvature is r2. Okay. Now, when this surface expands to this expanded surface, the radius of curvature would change according to this height delta z, right. So, this new radius of curvature here becomes 1 plus delta z over r1 into r1, right. Similarly, this radius of curvature changes from r2 to 1 plus delta z over r2 to into r2. Okay. Accordingly, the lengths of the sides, okay, from delta x it becomes 1 plus delta z over r1 into delta x, and this becomes 1 plus delta z over r2 into delta y. This is geometry, if you work out this is what you get. Okay. So, now you can say that the two local radii of curvature in two orthogonal directions becomes R I plus delta z, okay, will be equal to 1 plus delta z over R I into R I. So, we generalize this, okay. So, 1 plus delta z over R 1 into R 1, 1 plus delta z over R 2 into R 2, where I equal to 1 2, okay. Now, here I should mention that for any curved liquid interface, the radius of curvature is considered as positive if the center of that curvature lies within that medium, okay. So, that is a convention that is used, okay. So, here for example, the radius of curvature is here, and if it is within the fluid itself, then it is considered as positive. Now, the lengths of two sides change from delta x to 1 plus delta z over R 1 into delta x, and delta y change from 1 plus delta y changes from delta y to 1 plus delta z over R 2 into delta y, right. So, this is what we see here. So, the change in the area, the change in surface area delta A would become 1 plus delta z over R 1 into 1 plus delta z over R 2 into A, okay. So, delta x into delta y will be A minus A, okay. So, that is going to be the change in the area of that fluidic element, which will be nothing but, so you can write delta A as delta z over R 1 plus delta z over R 2, okay, into the area, right. Now, here we have neglected higher order terms, we have neglected higher order terms, right. Okay. So, when the interface expands, two things are happening. One is the surface energy is increasing, and the other thing is the pressure volume energy is going to reduce, because the volume is increasing and the pressure is reducing, okay. So, the total energy of the system, the change in the energy of the system, the change in energy of the system delta G can be written as delta G surface plus delta G pressure volume, okay. So, this is because of the increase in area and this is because of the decrease in pressure volume energy due to increase in volume, okay. So, we can write this. So, delta G will be equal to gamma into dA. So, that is the surface energy minus A into delta Z is the change in the volume into delta P surface. Let us say we have a surface, we have a pressure delta P surface exists across this interface. Okay. So, that becomes the pressure volume energy, right. So, if this is in equilibrium, if the interface is in equilibrium, then the change in the Gibbs free energy will be 0, right. So, this will be 0. Now, if you substitute for dA from here, okay, from 1, then you get gamma into delta Z over R1 plus delta Z over R2 into A is going to be A into delta Z into delta P surface. Okay. So, what we see here is delta P surface is going to be 1 over R1 plus 1 over R2 into gamma. Okay. Right. So, delta Z will cancel, area will cancel. So, this is what we would get. Now, so here what you see, delta P surface is 1 over R1 plus 1 over R2 into gamma. So, the Young Laplace pressure drop across an interface would depend on its radius of curvature across two different, we are talking about two different radius of curvature, in this case one axial and one azimuthal, and also its function of the surface tension gamma. Okay. So, here now if you look at this image, this is the image that you would see if you talk about a soap film suspended by two metal rings. Okay. This is one metal rings, this is another metal ring, and if you suspend a soap film, this is the structure that you would see. Okay. Now, the soap film is suspended between the two wires. So, the pressure across the film is the same. So, the Young Laplace pressure drop is going to be 0, right. So, we are talking about soap film suspended by two wires, rings. So, delta P across the surface both are atmospheric. So, is going to 0. Now, from this equation, from the above equation, from this equation you can say 1 over R1 plus 1 over R2 is going to vanish. Okay. Now, how this is possible? Is going to be possible because here we are talking about two radii of curvature. One is this radius, this we are talking about this R1, and the other is this radius of curvature which is R2. Okay. So, you can see here one, the center of one curvature lies within the liquid films and the other one lies outside. Okay. So, one is going to be positive, the other one is going to be negative. So, that is how they are going to cancel each other and the net pressure drop is going to be 0. Okay. So, with that let us move on and talk about another concept called contact angle. Okay. So, contact angle is another important property to be discussed when you talk about theory of surfaces. Contact angle is the angle between liquid gas and liquid solid interfaces, okay, at the contact line. Contact line meaning when the solid, liquid and gas 3 different interfaces come together. Okay. So, we talk about contact angle. And so, this exists at contact angle exists at contact line between solid wall and 2 immiscible fluids. Okay. So, how do we define contact angle? So, contact angle defined as angle between solid, liquid and liquid gas interfaces at the contact line where 3 different phases meet. Okay. So, we can say this is the solid surface and we have a liquid film present here. So, this is liquid and this is gas. So, the contact angle would be between the liquid gas interface and liquid solid interface. So, this would be called as the contact angle or theta. Okay. So, this is the contact angle and it happens at the contact line. So, this is the contact line which goes all around the perimeter where the liquid is in contact with the solid. Okay. Now you can see an example here. If you look at here, this is a case where the water drop is present on a pure silicon dioxide substrate in air. Okay. So, this is silicon water drop present on silicon dioxide surface and the contact angle is about 52.3 degrees, which is the theta that is shown here. Now, if you want to derive an expression for contact angle, it would depend on the surface tension between solid liquid, between solid gas and liquid gas value. Okay. So, the contact angle would depend on 3 different values of surface tension. So, the contact angle determined by surface tensions gamma solid liquid, gamma liquid gas and gamma solid gas. So, this is for solid liquid, liquid gas and solid gas. Okay. Now, if the liquid is stationary on a solid surface, then we can very well define what is the value of the contact angle. But if it is moving, then the contact angle would have 2 different contact angles, or in some cases there will be different values of contact angle around the contact line between the liquid and solid. So, if let us say droplet is moving, then the contact angle at the front surface, okay, front end will be different as compared to at the back end. Okay. So, there will be 2 different contact angles in that case. So, let us try to derive the expression for contact angle. So, for that let us consider a situation something like this. Here we have a solid surface, okay, and we have a liquid present in equilibrium, okay. So, this is the equilibrium interface, this is going to be the equilibrium interface, and let us say we subject this interface between liquid and gas to a minor perturbation, okay. So, this is the new interface for the liquid gas, okay. This is the perturbed interface. This is the perturbed interface, and when it does that, this contact angle from here it stays the same when it attains a new position. Let us assume that we are really looking at microscopic, we are taking a microscopic view at what happens at the contact line. So, in that case this interface at the contact line can be viewed almost constant, almost linear, okay. So, the contact angle here is the same at the displaced position, given that the displacement is elemental, very small, okay. So, this is the displaced liquid. So, in that case you can see that if you draw a normal from this point onto the gas liquid interface, okay, this is the normal. So, there are, because of the displacement of the liquid, the interface between liquid gas, liquid solid and solid gas are going to change, okay. So, so the changes in interfacial area so for the solid and liquid it is going to be plus delta L, and the liquid and gas is going to be delta L cos theta, and solid gas is going to be minus delta L, okay. So, this is going to be the changes in the interfacial area. Now, if you look at if we represent the surface tensions at here we can say that we have gamma solid liquid, and here we have gamma liquid gas, and here we have gamma solid gas, okay, and this angle is theta here, okay. So, what we can write here is we can do an energy balance at equilibrium, and we can assume that the width of this film into the plane is W. So, in that case we can say the the change in the energy per unit width is going to be gamma solid liquid into delta L, okay, what we see here, plus gamma liquid gas into delta L cos theta, then minus gamma solid gas into delta L, because this delta L is negative. So, you have a negative sign there. So, this change in the free energy is going to be 0 if you consider that the film is at equilibrium initially. Okay. So, in that case we can write here cos theta is going to be gamma solid gas minus gamma solid liquid divided by gamma liquid gas. Okay. So, this is how we can express the contact angle. Now, depending on the theta, if the theta is less than 90 degrees, we call this as hydrophilic. So, the surface is hydrophilic. If theta is greater than 90, then the surface is hydrophobic. Okay. So, this is the definition of hydrophilic and hydrophobic surfaces. So, with that let us stop here.